Hello, welcome to this video. In this video, we will solve one more problem on steady flow energy equation, our first law applied for an open system. The problem is, in a steam plant, 1 kg of water per second is supplied to the boiler. So, mass flow rate is given as 1 kg per second is supplied to the boiler. So, he is talking about a boiler. Now, let us say we have a boiler as our steady flow energy device. So, there is a boiler, and boiler must have water coming in and steam going out. So, anyhow, mass in and mass out. Okay. The enthalpy and velocity of water entering the boiler are. So, he has given enthalpy and velocity. So, H and V. Let me call it as inlet as 1 and outlet inlet of velocity as V1. So, 800 kilojoule per kg enthalpy. Enthalpy is 800 kilojoule per kg and velocity is 5 meter per second. The water receives, so water receives 2200 kilojoule per kg of heat in the boiler. So, water receives heat which is 2200 kilojoule per kg of heat. So, he is talking about the value of Q. So, heat received or heat supplied to the system is positive. So, I can say the value of Q is plus 2200 kilojoule per kg. So, it is better that we convert this into joule, that is into 10 power 3 joule per kg. So, Q is given at constant pressure. The steam after passing through the turbine comes out with a velocity of 50 meter per second. So, now he is talking about the velocity at the outlet. So, this was our 1 and 2, inlet is 1 and outlet is 2. So, steam after passing through the turbine comes out with a velocity of 50 meter per second, 50, and its enthalpy H2 is 2520 into 10 power 3 kilojoule is given. So, I am writing it as joule per kg. So, 2520 kilojoule per kg. Inlet is 4 meter above. So, he is talking about Z1 is 4 meter above the turbine exit. You can write it like Z1 is equal to Z2 plus 4 meter. Okay, Z2 plus 4 meter. Assuming the heat losses from the boiler and turbine. So, there is a boiler and then it goes to the turbine. That is what he means. So, there is a turbine next. Assuming the heat losses from the boiler and turbine to the surrounding. So, heat loss is there. We had supplied 2200 kilojoule per kg of heat, but there is heat loss also. So, heat loss. This was heat supplied. Okay. Now, heat loss is 20 kilojoule. So, minus 20 kilojoule per second. So, into 10 power 3 joule per second. Calculate the power developed by the turbine. So, we are supposed to find out the power, which is nothing but rate of work transfer, or W in other words, rate of work transfer. Consider boiler and turbine as a single system. So, anyhow, so we can consider this as our one single system. So, where does it matter? It matters in the calculation of Q, because heat one side we are supplying and there is heat loss is also there. So, while substituting it to the formula of first law of thermodynamics for an open system, our steady flow energy equation, we must consider the net Q, because there is supply and there is loss. Okay. So, let us start with the equation which we know, Q minus W is equal to change in enthalpy plus change in kinetic energy plus change in potential energy. Okay. Now, Q is given, let me write that Q dot here, because it is given in if you multiply this in joule per kg per second, we'll convert this into watt. So better, I'm writing it in watt here. So work transfer will also be in watt now coming. And this will be mass flow rate into H2 minus H1 plus mass flow rate into half into change in kinetic energy is given by V2 square minus V1 square plus change in potential energy multiplied by mass, just to keep it in joule per second, G into Z2 minus Z1. So this is the expansion of the same equation. Now Q should be substituted in watt, W should be in watt. Now if you substitute kg per second here and joule per second, this mass flow rate kg, joule per kg, H2 minus H1, then kg cancels out, you will have joule per second watts. So this will be in watts. Similarly here, mass flow rate in kg per second, and we know if you substitute this in meter per second, this will be meter square per second square. Meter square per second square is joule per kg, which we have already discussed in our first video. Meter square per second square and joule per kg, both are same. Okay. Now that will be kg goes off and you will have joule per second, watts here again, plus now again m dot is in kg per second and acceleration due to gravity meter per second square, and this is in meter square per second square is joule per kg again here. So unit is balanced, joule per second, again this is watt. Now this side also has to be watts and this side also has to be watts. So everything will be in watts, then the units are consistent. Okay. Now we will go on to substitute. Now what is given? Q. Let us solve this Q first. Q is plus 2200 kilojoule per kg, or now net Q, which we will have to substitute it here. Therefore, Q dot is equal to heat supplied in watts minus heat loss in watts. Okay, both should be in watts. So this has to be multiplied because first term is only 2200 into joule per kg. So into Q supplied in joule per kg minus heat loss is directly in watts. So this is minus. See, remember already we have substituted minus here, again do not confuse it, like do not add it. Okay, heat supplied minus heat loss. So minus, because it is already negative sign, we have already used it. Okay, do not use it like minus of minus. So this is okay, minus 20 into 10 power 3. Now this is in watts. Now remember this, we are substituting mass flow rate in kg per second and Q in joule per kg, then this will be also in joule per second, which is watts. Okay. So mass flow rate is 1, anyhow 1 is given, so that could not make any big difference, but still. So Q supplied is 2200 into 10 power 3. Alright. So minus 20 into 10 power 3 here. So this was in watts. Now let us solve this equation. One into this will be 1. So 1 into 2200 into 10 power 3 minus 20 into 10 power 3. So that will be 2.18 into 10 power 6. So in watts. So this is our Q. Okay. Now coming back to this equation, Q we have got it now. Q is 2.18 into 10 power 6. Okay. Minus W is what we want, and m dot is 1, that would keep 1 as it is. Now H2 and H1 should be given, yes, 2520 into 10 power 3 minus H1 is 800 into 10 power 3 plus 1 into half of V2 square V2 square is 50 square minus V1 square is 5 square plus 1 into G is 9.81 and Z2 minus Z1. So, we have Z1 minus Z2 here. Z2, now send this minus 1 here, Z2 minus should be equal to minus 4. So, Z2 minus Z1 from here can be minus 4. So, into 9.81 into minus 4. 9.81 into minus 4. Now, let us solve this equation. It is better to calculate each equation one by one and then let us substitute it separately. So, 1 I will leave 1 because 1 is going to give us the same answer 2520 into 10 power 3, 10 power 3 minus 800 into 10 power 3. So, that will be 1.72 into 10 power 6. So, the first term 1.72 into 10 power 6 plus half into 50 square minus 5 square. 1237.5. Now, this is negative here. So, I will just put negative here 9.81 into 4. So, 9.81 into 4. 1 will always be there. So, that will give us 39.24. And here on the other side, you have 2.18 into 10 power 6 watts minus W. Now, this would give us the rate of work transfer or what we call it as power. Now, let us solve this equation. 2.18 into 10 power 6 minus the unknown will always write it as alpha x. Now, alpha equals, I am typing the equation as it is. Alpha is what you use for equals. Now, 1.72 into 10 power 6 plus 1237.5 minus 39.24. Now, shift solve for x is equal to 0 and that is the answer which we wanted. 458.8 into 10 power 3. 458.8 into 10 power 3 watts. Or if you divide this by 1000, it will be kilowatt. So, 458.8 kilowatts. So, this is a combination of boiler and turbine. So, we are talking about work transfer. So, turbine should have work transfer and that net work transfer is 458.8 kilowatt.